research aircraft is the ultimate roller coaster ride, peaking at 34,000 feet over the Gulf of Mexico. The plane follows a parabolic flight path to produce weightlessness. A typical flight consists of about 32 arcs. As the plane climbs towards the top of the parabola, passengers feel the force of nearly 2 Gs, or twice their body weight. Once the plane starts to go over the top of the invisible arc and begins descending back toward Earth, flyers free fall, experiencing nearly 25 seconds of zero gravity. The passengers, and any objects not nailed down, are weightless.
The Vomit Comet is simply a nickname for any aircraft that can provide its passengers with a sense of weightlessness. It has been used to conduct research, train amateur astronauts, and for the pleasure of the American people, film movies. NASA, until 2004, had used the KC-135 for its training, but now, after 58,000 parabolas, the plane has unfortunately been retired and replaced by the new and upcoming C-9B Skytrain II. The KC-135, surprisingly, was also the site for the filming of Apollo 13, an American classic.
Hopefully everyone here has been on an elevator and been able to really experience physics at hand. Have you ever jumped in an elevator or felt your knees buckle when going up? At rest in an elevator, it's like any other scenario. The only forces involved are your weight and the normal force exerted by the ground. Going up in an elevator, you still exert the same weight, your mass times gravity, but because the elevator accelerates upward, and because your body, by inertia, wants to stay in place, the elevator must exert a larger force on you to get you to move upward. Therefore, the normal force is much larger, which directly results in a greater apparent weight, and subsequently a higher reading on the scale. On the other hand, going down in an elevator, your body again wants to stay at rest by inertia, but the elevator accelerates downward, so the forces between the two, the floor and the person, is reduced. So, less normal force is applied upward by the elevator to support the person's weight. Thus, the scale reads a lower value, making your apparent weight less. In the final case, if the elevator cable were to unfortunately snap, you and the elevator would both be in free fall, an acceleration of 9.81 meters per second squared, making yourself feel weightless inside the elevator, considering the elevator blocks all air resistance.
The Vomit Comet follows a parabolic path, and you feel weightless near the top of each parabola. As the pilot approaches the top of the parabola and zero gravity zone, he reduces the thrust so that the y component of his acceleration is equivalent to gravity, thereby putting the passengers and plane in free fall. The strong aircraft blocks all air resistance to the passengers, thereby simulating a weightless environment. This lasts for about 25 seconds because the plane must level out and start a new parabola, so it does not crash into the ground. Imagine yourself sitting on top of a chair. The chair exerts a normal force on you because of your weight. If you jumped off a cliff with your chair, you and your chair would be in free fall. In reference to your chair, you would appear weightless because your chair and you fall at the same rate. Going up in the plane, passengers experience 2 times the acceleration of gravity because, just like the elevator, your mass times the acceleration of the plane upward plus your weight would make a larger normal force on you, making you feel heavier.
Undoubtedly, people feel weightless in space. But the question is why? First of all, in space, everything is falling towards the Earth. Objects in space feel weightless not because there is no gravity in space. In fact, in space there is still the gravitational pull from the Earth, but it's not exactly 9.81 meters per second squared. It's about 11% less than 9.81, about 8.72. Whether it's a drifting astronaut or an AT&T satellite, everything is in free fall towards the Earth because of gravity's existence, making them feel weightless, as shown in the elevator or the plane. But objects don't rain down on Earth because of their extremely high orbiting velocity. That is to say, the centripetal force keeping objects in orbit is the object's weight from gravity. But as said, because these objects orbit going speeds like 8,000 meters per second, they're not going to fall and hit the Earth.
It's time for the pre-flight briefing with in-flight info from Zero G's Elizabeth Underwood.
Elizabeth, now that we're just about to go on, I want to know, how good a simulation of zero gravity is this?
It's not a simulation at all. It is the real deal. It's the exact same technique that NASA's been using to train their astronauts for the last 50 years.
And it works like this. A series of parabolic arcs will give the passengers the physical sensation of weightlessness. And just for us, the pilot will adjust the angle of the parabola, making the microgravity in the cabin an exact match to the moon's gravitational pull, which just leaves the guys to step up, strap in, take off, and suit up.
I look good, right? Good. I look damn good. So right now, I'm loaded up with an extra 180 pounds on my body. In a few minutes, we're going to actually get to try this out in moon's gravity, and I got to tell you, I can't wait. This is a heavy suit.
Adam doesn't have to wait long because the guides soon have everyone into position for the first pass. And as G-Force 1 gently arcs into its dive,
Oh, that feels cool.
Adam and Jamie
Oh, here it comes.
know what it feels like to walk on the moon.
Whoa. Wow. That's 100% wacky right there.
Calibrated to match the moon's gravitational pull, the guys just get time to take it all in before the call goes out to hit the deck. Because as the plane begins to pull out of the dive, the G-forces go into the positive.
There is a cost to being weightless. The other end of the roller coaster, you've got almost twice Earth's gravity. That's kind of terrifying at first, isn't it?
Yeah, it is. I'm blue, I've been